Okay, in triangle, if A, B, C are vertices and H is orthocenter, then A, B, C and H form orthic group of points. What do we mean by orthic group of points? If you choose any three of those 4 points and create a triangle, the orthocenter of that triangle is going to be the 4th point, because orthocenter of triangle ABC is H, orthocenter of triangle HBC is A, HCA is B, and so on. So this is important. So if you have been given 3 vertices and asked for find orthocenter, is equivalent to saying find A if H, B and C are given. It is one and the same. So let us find orthocenter of triangle ABC, where A is 2, 2, B is 4, -2, C is -5, -5 in 3 different ways. Okay, first find out by one method and then we will find out by 2 different methods. The fastest method in this case would be find the equation of AD, find the equation of BE and get the point of intersection. Okay, so first method is find equation of AD and BE and get point of intersection. Okay. Maybe a little long, but we just do it by some other methods. Can we quickly write down equation of AB now? What is equation of AB? Slope is 4 upon -2, that is minus 2 is the slope, therefore 2x plus y is equal to 6 is the equation of AB. Equation of BC, -2 plus 5, that is 3 upon 9. 1 by 3 is the slope, therefore x minus 3y is equal to -5 plus 15, 10. 4 and equation of AC is slope is 7 upon 7, that is 1, x minus y is equal to 0, right? These are the slopes. Okay, so I am just trying to use L1 plus lambda. So AB is a line and AC is another line. So 2x plus y plus lambda 1 times 2x plus y minus plus lambda 1 times x minus y is equal to 0 is all lines passing through A. Correct? So it is 2 plus lambda 1 times x plus 1 minus lambda 1 times y minus 6 is equal to 0. So what is the slope of this line? 2 plus lambda 1 upon minus 1 minus lambda 1. This is the slope of this line, general line. And with what slope we want? We want slope which is perpendicular to BC. So 1 by 3 is the slope of BC. So minus 3 should be the slope of AD. That gives me value of lambda. 2 plus lambda 1 is equal to 3 minus 3 lambda 1. So 4 lambda 1 is equal to 1. Therefore, lambda 1 is equal to 1 by 4. That gives me, I'm just doing it for academic purpose. It's a very long process, but anyway. So if I put it 1 by 4 here, I get 8x plus x, that is 9x. 4 बचा 1 plus 3y 24. I have achieved only AD right now. This is AD. And AD is 3x plus y minus 8 is equal to 0. Maybe if you have been given 3 lines like this instead of given 3 points, if 3 points are not given but 3 lines are given, this method might be worth going about it, because you don't need to really find out the points of intersection. Okay, so 3 different ways. These 3 different ways are little long, but what I was trying to tell you is, if 3 points are given, then whatever method you have adopted is the best method for finding out the orthocenter, which is correct. But if 3 lines are given, maybe use L1 plus lambda L2 is equal to 0 to find out AD. Similarly, BE, and get the point of intersection. In that case, you need not find out the points of intersection of these 3 and go back to this. You can directly get it. And the third method that I wanted to discuss, we have derived it last lecture. First, let me ask you to find circumcenter of ABC. How will you find the circumcenter of this triangle? If A, B and C are given, one way is to go from orthocenter, centroid and circumcenter. Second way to go is to find out midpoint of these 2 lines and get the lines perpendicular to them. Find the equations of perpendicular bisectors 1 and 2 to get ortho, to get circumcenter. So tell me, what is circumcenter of this triangle? Okay, by that method, whatever method you have used, but if you have used perpendicular bisector method, you must have got circumcenter O as -1, -2. Okay. Therefore, now let us find out orthocenter using shift of origin. So if we shift origin to -1, -2, what will be the new coordinate of A? Old coordinate of O was -1, -2. New coordinate is 0, 0. So old coordinate of 2, 2. What is new coordinate of A? Sanga? What is new coordinate of A? 3, 4. What is new coordinate of B? 5 comma 0. What is new coordinate of C? Bola -4 comma -3. Now, is the circumcenter at origin? Yes. Therefore, after shifting the origin, orthocenter is 5 plus 3, 8 minus 4, comma 4 plus 0 minus 3 is 1. This is after shifting the origin. Therefore, orthocenter before shifting the origin should have been -3, -1, which is same as what you have found out here. Right? Do you understand? So, by any chance, if you happen to know the circumcenter, in present problem we have to find out the circumcenter. So instead of that, we might as well find out the orthocenter because orthocenter is asked. But this sometimes becomes very handy. If you know the circumcenter of triangle and if you are asked to find out orthocenter, then this sometimes becomes very, very useful. Here, when the circumcenter is at origin, orthocenter is summation of x coordinates, comma summation of y coordinates. That is the point that I wanted to make in the end of last lecture. I hope you have understood. जरा लिहून घ्या आणि क्रॉस चेक करा माझं शिफ्ट ऑफ ओरिजिन बरोबर आहे की चुकलंय ते.
Oh, sir.
Okay. Sorry. Mistake. H should be +4, 1. And then if you then what is the orthocenter? Actually you are getting 3, +3, is that right? +3, I mean you have to subtract 1 and subtract 2. Okay, this is the orthocenter that you have found. Mistake. Let us do theory. Theory of straight line. In fact, this should have been done in the beginning of coordinate geometry, but if I go into the theory of straight line and do lot of abstract algebra, then you might not be able to understand what is happening. Therefore, we dealt with numericals first, and I am trying to legalize all the things that we had done earlier by writing couple of proofs, couple of theorems in straight line circle, two-dimensional geometry, whatever we have studied so far. Now, in geometry, we said straight line is undefined. I mean, we don't try to give definition of point or a plane, right? That is what is the Euclidean geometry. Don't define these sets. We say that we understand them and they are very, very trivial concepts, easy concepts to understand. Therefore, we don't get into defining these basic concepts and we assume it to be undefined terms. Okay. But another approach is, suppose if we study coordinate geometry first and say anything looking like ax plus by plus c is equal to 0 algebraically, where x and y are real variables and a, b, c are parameters, and at least one of a comma b is not equal to 0, then that set of points which satisfies this algebra is a straight line. One can define straight line by coordinate geometry way. So what is really first that you do, and whatever you do first, you have to assume few things in that. And using those things, you can really develop the definitions or develop the concepts in the other form of mathematics. So because we studied Euclidean geometry first, We said a straight line is undefined term, and from there we started and we developed the entire geometry. And if I want to find out how does the algebraic equation of straight line looks like, which we assume that it is going to look like this and solve many problems, but this is the time where we are going to derive it. So I will take help of geometry. And in geometry, I definitely know that if I have a segment AB whose say coordinates are x1, y1 and x2, y2, and if I find out locus of all the points equidistant from A and B, I know geometrically that locus is a straight line which is perpendicular bisector. So I am familiar with this locus. I am familiar with the geometry of this locus, but I don't know what is the equation of straight line, how it looks like. But I know how to solve a locus problem. Therefore, I consider any point P, x dash, y dash on the locus, and the geometric condition is PA is equal to PB. I use that geometric condition and try to develop the algebraic expression for the perpendicular bisector, which happens to be the straight line. Do you understand this? I am going to try and make it as simple as possible, because normally these discussions are heavy because they are abstract algebra and you are too young to understand them. But if you pay proper attention, you will understand everything that we do today. Okay, and that is where we differentiate ourselves from other institutes, that it is okay if I don't do it also, but we want to do it. As simple as that. Okay, so I know the geometry of straight line. I know a special line which is perpendicular bisector, which is a straight line. I am sure about it, and therefore using coordinate geometry I would like to develop the equation of perpendicular bisector and observe it, whether it is degree 2 equation, degree 3 equation, linear equation in X, how is it? And then I will realize that a straight line in two-dimensional geometry looks like this. Okay, so what these calculations we have done earlier, but I will do it quickly now so that we complete the theoretical part. Okay, so the locus problem, P x dash comma y dash belongs to desired locus. Let P x dash comma y dash belong to desired locus S. Locus S is the set of points which satisfy the given geometric conditions. Okay, so what will be the first step? Pa square is equal to pb square. So x dash minus x1 bracket square, y dash minus y1 bracket square is equal to x dash minus x2 bracket square plus y dash minus y2 bracket square. If you simplify this, which you have already done, we will get 2 times x2 minus x1 times x dash plus 2 times y2 minus y1 y dash is plus x1 square plus y1 square minus x2 square minus y2 square is equal to 0. Now x1, y1, x2, y2, they are distinct because A and B are the endpoints of the segment. Therefore, we know x1, we know y1, they are real numbers. So x2 minus x1 happens to be a non-zero real number. Y2 minus y1 happens to be a non-zero real number. Therefore, 2 times x2 minus x1, I can call it as A, x dash plus b, y dash, and this is also a real number, plus c is equal to 0, replacing x dash by x and y dash by y, we get desired locus. And therefore, equation of this locus is ax plus by plus c is equal to 0, which happens to be the straight line. Therefore, we have arrived at, if we know that the locus is a straight line, its equation looks like linear equation in x comma y. Algebraically, we have to say it looks like ax plus by plus c is equal to 0, where at least one of a comma b is not equal to 0. If both a and b are 0, then it is constant c is equal to 0. Does not make any sense at the moment, but we will try to figure out what does that mean, because we have come across that situation while solving the problem of the tangent. Okay, this stage either a or b is not equal to 0, or both of them are not equal to 0. Okay, at least one of a comma b is not equal to 0, and both of them can be not equal to 0. That is what is the first part of the coordinate geometry. We wanted to find out algebra of straight line. If you remember, I said I have a point here and I have a point here, and how do I know whether this point is on this line or not? So the answer to that is, you find out equation of this line and substitute this point back into this equation and check whether it satisfies or not. Now this is part one of this result. Okay, so if p x dash comma y dash, that is basically the converse and direct theorem. If p belongs to S, then this happens. Now if I have, suppose, a new, if I have a new point, now I am not going to write the part 2, that is converse of this, I am just trying to explain it. Suppose I have a point p whose coordinates are x0 comma y0, and I say ax0 plus by0 plus c is equal to 0. So algebraically I know an ordered pair x0 comma y0 which satisfies this equation, that is this equation. So every step is reversible in this case, and there I can go back from here to here, that is what is this step, from here to here by doing, by replacing a by these two if one point satisfies this, px0 comma y0 satisfies this, then I can always go back. Instead of AB from here, we are just doing it to show that it is linear. Okay, we are showing. So if x0 comma y0 satisfies this equation, then here it will be x0, here it will be y0. You can regroup them, you can add the deleted terms like x dash square, y dash square, etc. Make it a complete square. So from here to here you can go writing, instead of x dash and y dash, we will have x0 and y0 in this place, and then we can look at it as a distance, and the geometric condition is satisfied. Therefore px0 comma y0 will belong to S. Okay, so that is what I am trying to tell you, that if a point is satisfying the equation of curve algebra, then it is on that geometry, and if any point from the geometry is picked up, then it must satisfy this algebra. That is one relationship that we have discussed in the first lecture of coordinate geometry. We have designed XOY plane such that every point is designated distinctly, and every point P x0 y0 will have some geometric presence. Just a moment. Answer. Okay. So every point on a plane, if it belongs to some geometry, then it coordinates of that point will satisfy the equation of the curve and vice versa. That is what is the first lecture of coordinate geometry. Okay, so we have observed that in case of straight line. Now, whatever we are saying right now, there is one catch to it. For example, in simple words, if I want to explain it to you, suppose I have a line, geometrically this is the line in XY plane whose equation is 3x plus 4y plus 5 is equal to 0. And it geometrically, if I draw, it is this line. Now, if I multiply this equation by say minus 1, I get minus 3x minus 4y minus 5 is equal to 0. This equation algebraically is not same as this, because when I write this, I write it like f1 of x comma y is equal to 3x plus 4y plus 5, and it happens to be equal to 0. That means this curve is equal to 0. This algebra is equal to 0, represents some geometry, and I said that is this geometry. But then this is different. f2 of x comma y is equal to minus 3x plus 4 minus 4y minus 5 is equal to 0. So this is not equal to this. However, the geometry of both these curves is same. That is the catch. Now, you need to understand this very well, because you might be in trouble a little later. Every time will it happen like that? Let me write down the theorem for that. It's let S1 be solution set of f1 x comma y is equal to 0. Let k belong to real number, k not equal to 0, full stop. Let f2 of x comma y is equal to k times f1 of x comma y. Let S2 be solution set of f2 of x comma y is equal to 0. Then S1 is equal to S2. Okay, this is the technical description of the theorem. It is very simple. Just understand. S1 is a set of points. E is a solution of f1 x comma y. We can always take an example and check. f1 x comma y is my this expression. It is equal to 0. And S1 is a solution set. So I can call this straight line as S1, solution set of f1 x comma y. I multiply by non-zero constant k. K is a real number which is not equal to 0. And I get another function f2 x comma y. In our example, f2 is this. f2 is equal to minus 1 times f1. Suppose, let us say, suppose S2 is a solution. Suppose S2 has a different solution set. Suppose S2 be a solution set of f2 x comma y is equal to 0. This theorem says no, it is not possible. S1 will be equal to S2. Is this theorem intuitively acceptable to you? Let me stop recording and okay, intuitively this particular theorem is Very easy to understand. Solution set for this and solution set for f2x comma y, they are going to be same. If we really want to write down the proof of S1 is equal to S2, we need to use set theory, and to show two sets are equal, what we need to do is, which we will study in 11th and write the proof. S1 is a subset of S2 and S2 is subset of S1, then S1 is equal to S2. We have to use this. So you take any representative point P x1 y1 from S1, show that it belongs to S2, and it is easy. If S1 P x1 y1 is in S1, it satisfies this equation. That means F1 x1 y1 is 0. That means K into F1 x1 y1 is 0. That means F2 x1 y1 is 0. That means point P belongs to S2. If we take another point Q x2 comma y2, which belongs to S2, then it satisfies this equation. If it satisfies this equation, and if k is not equal to 0, then it satisfies this equation. If it satisfies this equation, then it belongs to S1, and therefore S4 we can show for every point in S1 it is a subset of S2. For every point in S2 it is a subset of S1. Therefore S1 is equal to S2. This is easy. Okay, and it is if and only if. This is easy, we can prove it in both the ways, and therefore we can show that S1 is equal to S2. Now the most important theorem that we are going to do, which is little long, but we will write complete correct proof, is as follows. Here, maybe you simultaneously write down this in your notebook, because it has to be there in your notebook. Important, consider. The first degree equation a1x plus b1y plus c1 is equal to 0 in x comma y. This is our equation 1. Let S1 be solution set of 1. Consider the first degree equation a2x plus b2y plus c2 is equal to 0 in x comma y. Let S2 be solution set of 2. Let a1 x1 y1 and a2 x2 y2 be two distinct points in S1 intersection. This is our statement number 3. Then there exists K belonging to R, K not equal to 0, such that A2 is equal to K1, B2 is equal to KB1, and C2 is equal to KC1, and S1 is equal to S2. Okay. Okay, what we have done in the beginning today is we have found out the equation of perpendicular bisector, right? And there we knew that perpendicular bisector is a straight line, and we have proved that if it is a straight line, then its equation looks like ax plus by plus c is equal to 0. That is linear in x and y. So one way it is proven, if it is a straight line, then its equation looks like ax plus by plus c is equal to 0. Now our efforts right now, what we are doing is, if we want to prove every degree 1 equation in x and y, we wish to prove the otherwise. If any equation in x and y is given to us, every equation in x and y is given to us, which is linear, that means it is of the form a1x plus b1y plus c1 is equal to 0. No matter what these coefficients are, if the power of x is 1, power of y is 1, and constant term, that means power of x comma y, any of them is 0. So that is what is linear. If every degree 1 equation in two variables represents straight line, that is what we want to prove. We have proved perpendicular bisector if geometry. If perpendicular bisector, then equation looks like ax plus by plus c is equal to 0. What we are trying to prove now is, if equation of some geometry looks like ax plus by plus c is equal to 0, that is linear equation in x and y, then we are trying to prove that it must be a straight line. It must be a straight line. This way we are trying to prove, and therefore it is little involved proving this. So for proving this result, whatever we are saying, we want, this is a prerequisite theorem. Now we don't know whether this is a straight line or not. This is the stage we are in right now. Suppose we don't know what is this is a straight line or not. So for deliberately for this purpose, I say that this is the equation, this is the geometry of equation 1. Is a1x plus b1y plus c1 is equal to 0. Looks like something like this, suppose, if possible. Okay. So this is what is S1. That is the second line. Let S1 be the solution set of 1. So geometrically, suppose S1 is looking like this. Then the third line is, consider another degree 2 equation, which is different than this. Okay. So let me consider another degree 2 equation like this. I don't know how this geometry is going to be. We are eventually going to prove that this geometry has to be straight line. But right now we don't know. So I am assuming that this first degree equation, which is second equation, looks like this. Its geometry S2 is like this. And the equation is a2x plus b2y plus c2 is equal to 0. Okay. So therefore, I am considering that if these are the two solution sets of these two equations, and if they have more than 2 points in common between them, okay. So I am assuming that this point is A1, whose coordinates are x1, y1, and this point is A2, whose coordinates are x2, y2. Because these 2 points are common to both these lines, they are two distinct points in the intersection. S1 intersection S2. In this diagram, I have taken only 2 points, but it can be more. I mean, if I consider S1 like this and S2 like this, then there are more than 1 points which are common. Okay, but I am considering the simplest geometry, maybe just to understand what we are doing, and therefore A1 and A2 are two distinct points. Distinct word is important in S1 intersection S2. So if A1 belongs to S1 intersection S2, A1 satisfies both these equations. A2 belongs to S1 intersection S2, A2 also satisfies both these equations. That is what is the prerequisite of this theorem. So if it is so, then there exists K belonging to real numbers such that A2 and A1 are going to be related to each other by constant. Okay. Now, That is precisely what we have done here. We have multiplied by non-zero constant. Therefore, A2, this is A2, this is A1, and A2 upon A1 is -1 in this case. So, if it is linear in X and Y, then they are going to be, and if they represent the same geometry, then their coefficients are going to be proportional to each other. Okay, just to explain this more, I will take yet another example. Suppose I have an equation which is not linear, which is higher degree, say x cube or maybe x4 plus x raised to 6 is equal to 0, or x4 plus y raised to 6 is equal to 0. And another equation, so this is f1 of x comma y. f2 of x comma y I consider as 2x square plus 7y raised to 4 is equal to 0. Okay. So I am just giving you two algebras, two algebraic expressions. Now can you visualize and tell the geometric solution set of this equation? This is algebra. What is corresponding geometry? What is S1 and what is S2? Can you visualize and tell me what is S1 and S2? Now this is x is a real variable, y is a real variable, and it is fourth power. Here it is sixth power. Therefore, this is going to be non-negative number. This is going to be non-negative number. They are getting added to become 0, and therefore each one of them must be 0. So solution set S1 is the only point in 0, 0 in this case. 0, 0 is the only point which will satisfy this. No other point. What is the solution set of F2, S2? Origin 0, 0. So here S1 is equal to S2. Both the solution sets are same, but F1xy and F2xy, they are altogether different because the degree of these equations is other than 1. Other than 1. If degree of these equations, LHS equations, is 1, that means they are linear, then this cannot happen. Then what will happen? If degree 1 of x comma y is 1, that means it looks like this: a1x plus b1y plus c1 is equal to 0. If this linear in x and y will look like this, and it is f1. Whatever is the solution set of this, f2 x comma y, it looks like a2x plus b2y plus c2 is equal to 0. Whatever its solution set looks like. But if solution sets are same, as if S1 is equal to S2 of this as well as this, then indeed that A2 upon A1 is going to be equal to B2 upon B1 is equal to C2 upon C1. Situation like this will never happen in linear equations in X and Y. Now I can produce infinitely many LHS equations which are not, coefficients are not proportional to each other, but the solution set is same. Geometry of this algebra is origin. Geometry of this algebra is origin. But if it is linear in X and Y, if geometry of this is S1 and if geometry of this is S2, and if you have two intersection points common between them, then S1 must be equal to S2 and the coefficients are going to be proportional. That is the meaning of this theorem. Okay. Now what is left is pure algebra to show that they are proportional and therefore S1 is equal to S2. Okay. So you note down this. This is a very special example which I have given you to explain that algebra is different but geometry is same. And if it is not degree 1, then coefficients need not be proportional. But if it is degree 1, coefficients must be proportional. If S1 is equal to S2, then coefficients must be proportional. However, in this, what we are going to do, because it is straight line, and if it has 2 points common between them, the entire S1 is going to be equal to S2, because we know geometrically 2 points determine a line. If there exists a straight line passing through 2 points, then it is the same straight line for this, and it is going to be same straight line for this, because it is the geometry passing through A1 and A2. Okay, so you note down this example, then I will erase this red part and write down the proof of theorem. Okay, so now let us write down the proof. I have already written the proof, explained it once. Now let me explain it for the recording. We start with first showing, assuming that which okay, without loss of generality, let A1 is not equal to 0. A1 belongs to intersection, therefore A1 satisfies equation 1. Equation 1 is this: A1x plus B1y plus C1 is equal to 0. Okay, so A1x1 plus B1y1 plus C1 is equal to 0. A2 satisfies again the equation number 2, A1x2 plus B1y2 plus C1 is equal to 0. You subtract these two equations, we get A1x1 minus x2 plus B1y1 minus y2 is equal to 0. If y1 minus y2 is 0, then x1 minus x2 is 0, because we have assumed a1 is not equal to 0. Therefore, x1 minus x2 also happens to be 0, and hence a1 coincides a2, which is contradicting the statement number 3 of the theorem, that we have assumed a1 and a2 be two distinct. Okay, therefore y1 is not equal to y2, or y1 minus y2 is not equal to 0. Now, a1 belongs to the intersection, therefore a1 satisfies both the equations. a1 x1 plus b1 y1 plus c1 is equal to 0, and a2 x2 x1 plus b2 y1 plus c2 is equal to 0. So here we will try to eliminate x1, and if we want to eliminate x1, we multiply first equation by a2, second equation by a1, and subtract. After doing that, we get a2b1 minus a1b2 times y1 plus a2c1 minus a1c2 times that is the constant is equal to 0. Okay, similar work if we do for a2, then we get a2b1 minus a1b2 times y2 plus a2c1 minus a1c2 is equal to 0. Now if we subtract equation 4 and 5, we get a2b1 minus a1b2 times y1 minus y2 is equal to 0. But y1 minus y2 is not equal to 0. Therefore, a2b1 minus a1b2 should be equal to 0. Implies a2b1 is equal to a1b2. That means if a1 is not equal to 0, I can always divide and get a2 upon a1 is times b1 is equal to b2. That means b2 is equal to k times b1, where k is a2 upon a1. हे उठते का आज काय कळत नाही मला. Just going out. Okay. By putting this equation 6, whatever we have achieved, back into equation 4, we could find out C2 as A2 upon A1 times C1, which is K times C1. And A1 is also K times A1. So that completes our first part of the proof. And then second part of the proof is, if we consider that F2, second equation, then it becomes K times first equation, and therefore the solution set for first and solution set for second must be same. Therefore, we cannot afford to have some curves like this, the solution sets must be same. So here what we are saying is, if solution set for first is like this, S1, And suppose A and B, A1 and A2 are the points on S1, then here what we are trying to say is the solution set for S2 is also same. Okay, it is also same. Now I will write one small theorem which will show that if there are 2 points and a linear equation is passing through them, then it cannot be the curve like this. It has to be a straight line passing through A1, A2, and that will complete our total job that we are trying to do. Every linear equation in X and Y is a straight line. So let me finish this by writing a small theorem where I will use this theorem again to prove that theorem, and then our job will be over. I am aware this is little heavy for you at this stage, but this is important. I mean, you need to have practice of some learning something which is why is it dancing today? The whiteboard also has some problem today receiving this content. Okay, so the last theorem is maybe the last theorem or today is this. Every first degree in X and Y theorem, every first degree equation in X and Y represents straight line in XY plane. Okay, that is what eventually we wanted to prove. So let me straight away write down the proof. Consider the first degree equation a1x plus b1y plus c1 is equal to 0. Let S1 be solution set of 1. Without loss of generality, let A1 not equal to 0. Let Y1 not equal to Y2 and Y1 comma Y2 belong to R. Okay, clearly A1 is minus B1 Y1 plus C1 upon A1 comma Y1, and A2 is minus B1 Y2 plus C1 upon A1 comma Y2 belong to solution set S. Now let not be S1, let it be only S. Okay. What is the point up to this? Suppose we consider any first degree equation. We don't know whether it is straight line or not. We are considering first degree equation a1x plus b1y plus c1 is equal to 0. And whatever is its solution set, whatever points does this equation represent in xy plane, we call it as S. It's a linear equation in X and Y, therefore I am free to consider either A1 not equal to 0 or B1 not equal to 0. I have started with A1 not equal to 0. Okay, and hence I consider two Y values, two real numbers, Y1 and Y2, two distinct real numbers, Y1 not equal to Y2, they are real numbers. If I plug those values of Y1 and Y2 back into this equation, I will get values of X x in both the cases. Maybe we can call them as x1 and y1, x1 and x2. So if I put y1 here, then I can find out x as minus b1 y1 plus c1 upon a1. That is what is this point. So I am trying to get 2 points on the on this curve, which is part of this set. So I am trying to get 2 distinct points belonging to this set S. Okay, so I have achieved those 2 points now. Now note that A1 is not equal to A2. Now let A2x plus B2y plus C2 is equal to 0 is the equation of line. I mean, if I have 2 points, 2 distinct points in xy plane with me, I can always have equation of line passing through these two, which we have already done earlier. If I have been given 2 points, I can find out the equation of line. So let the equation of line be a2x plus b2y plus c2 is equal to 0 be the equation of a1 a2, straight line a1 a2. Okay. So now what has happened? We have got 2 distinct points out of this linear equation in x and y. Know whether this is straight line or not. It has this solution set. We got 2 distinct points. After we got 2 distinct points, we can always find out equation of line. Suppose it looks like this. Again, it happens to be linear in x and y. Okay. So now we have 2 equations linear in x and y. Solution set of this is S and solution set of this is straight line passing through A1 and A2. Okay, and therefore by previously proved theorem, if there are two equations, linear equations like this, then S1 is equal to S2. Hence, by previously proved theorem, or maybe let me write down a couple of sentences in between so that it becomes more clear. Note that it is a first degree equation in x comma y. Hence, a1 and a2 are two distinct Okay, so let me just try to explain it again. We have been given a first degree equation a1x b1y plus b1y plus c1 is equal to 0. Let the solution set be S without loss of generality, and we could find out 2 points using this equation. We could find out 2 points on 2 points which belong to this S, two distinct points. A1 is not equal to A2. So the moment I have two distinct points, I can always find out the equation of straight line passing through that. And suppose that looks like this. So my first solution set is S, and my second solution set of this is line A1 and A2. Line A1 and A2. However, A1 is part of this solution set S, and A1 is part of line A1, A2. A2 is part of this solution set S, and A2 is part of line A1 and A2. Therefore, it satisfies the previously proved condition requirements of theorem, which is previously proved. Exactly same situation. Therefore, A1 belongs to S as well as A1 belongs to line A1, A2. A2 belongs to S and A2 belongs to line A1 and A2. Therefore, and both these equations are linear in X and Y. Therefore, S must be equal to line A1, A2. That is what is the final statement that we are writing here. Okay. So, whatever we have discussed today, everything put together, we get the final result that every first degree equation in X and Y represents straight line. This is what we had assumed and we solved all the problems. But somewhere, someday, somebody has to prove this, that why should every first degree equation represent straight line? It's okay if you try to find out equation of straight line, it looks like first degree equation in X and Y. But why is converse true? So the total discussion that we have done today and total proofs that we have written today proves the converse, and this is the converse. Every first degree equation in X and Y is a straight line in XOY plane. That is what is this. I am aware that it is involved and requires lot of energy to understand this proof, but you are fortunate that the proof is available in written in front of you, as well as you can run through this video as many times as you want. So I am stopping right now.